We want to be able to talk about more complicated continuous functions. And so we have all kinds of continuity theorems. And again, continuity is one of the deepest and most important ideas in all of mathematics. So there's really no limit to the number of continuity theorems one could prove. But we'll just introduce a couple here so we can build up a framework of continuity to use as we move forward with the functions we encounter in calculus. Let's start with a theorem that begins to build up the algebra of continuous functions. If you look at the space of all continuous functions, it turns out it has a really nice algebraic structure to it. And mathematicians study this, right? There's a whole branch of mathematics where you can kind of study the algebra of continuous functions, and lots of people do so. So what can we do with continuous functions? Well, if we add them together, we still get a continuous function. So this theorem says if f and g are continuous at a, then the following are also continuous. F plus g, right? We can add two continuous functions together, we still get a continuous function. Same thing when we subtract them, when we multiply them by a constant, that's important. That's part C there. Part D, we can multiply two continuous functions together, we still get a continuous function. Part E says we can divide them, so getting our algebraic structure going here, as long as that g is not 0 at that point A. And we can take them to some integer n. We can raise them to powers. Well, we know that the function x is continuous, right? Just imagine f of x equals x. We could use our continuity checklist on that and pretty easily get that f of x equals x. But then using a, let's see, b would be helpful, c, and f, we could use those to show that all polynomials are also continuous. Because polynomials are nothing but taking x to various powers. Let's just do an example. I don't know, 5x cubed plus 2x squared plus x minus 3. So all it is taking x, and then we have it to various powers here. So we're doing f, multiplying it by constants, 5, 2, 1, etc., and then adding and subtracting things together. So from this, we can see that polynomials are continuous. Well, then E tells us that if we divide two continuous functions, we get another continuous function. So from that, we can tell that rational functions are continuous. So we say rational functions of the form p of x over q of x, that's how we usually talk about rational functions, are continuous, and of course provided that, we'll say q of x in this case, does not equal 0. And we can go on and on like this and build up a list of continuous functions, so let's bring up such a list. The following functions are continuous on their domains. Polynomials, we talked about that one. Rational functions. Trigonometric functions, also, you can make an argument as long as you're on the domain of trigonometric functions, they remain continuous. Inverse trigonometric functions, same thing. As long as we're in the domain, those are going to be continuous. Exponential functions, logarithmic functions, radicals of the form f of x to the 1 over n power, absolute value, and many more, right? We could go on and on listing continuous functions, and you can construct some pretty bizarre functions, and when you do so, a lot of math is about doing that. One of the first questions you want to answer is this thing continuous? And even when you expand this to different mathematical spaces, you come up with new definitions of what continuity means in those spaces, and then any transformation you create between two mathematical spaces, you ask whether or not it is continuous based on whatever definition of continuous you're using for those spaces. So really, we have this list of continuous functions that we'll use for the remainder of calculus and beyond, but it's certainly not an exhaustive list. One more important point about continuous functions is the continuity of composite functions or compositions. So here's a theorem, continuity of compositions. If g is continuous at a point A and f is continuous at the point g of A, then the composition f of g is continuous at A. So what this tells us is we can stack continuous functions inside each other and still have a continuous function. So let's just see, maybe I wanted to do sine. We know sine's continuous on its domain of, let's do a polynomial in there, x squared plus 3x minus 7. Okay, so now we have a polynomial, which we know is continuous, inside sine, which we know is continuous on its domain, which is everywhere. So this theorem here allows us to say that this thing is also continuous. Right? We don't want to have to keep expanding our list of functions to now say, oh, trigonometric functions with polynomials inside them are continuous. Right? Our list would never end. It would just go on and on. So with this theorem, we can say, all right, you can put a continuous function inside another continuous function, and the whole thing is still continuous. So let's use these theorems to work out some examples. Determine the intervals on which the following are continuous. And the first one, A, gives us f of t equals t plus 2 over t squared minus 4. That's a rational function, which we know from the previous theorem is continuous on its domain. So essentially, we just need to find the domain of this thing. Well, we can factor out that denominator. So that gives us t plus 2 over t plus 2, t minus 2. And remember, you don't want to cancel before finding your domain. So right away, I can see that there's two forbidden values, anything that's going to give us 0 in the bottom. So t does not equal plus or minus 2. So I'd say everywhere else, this function is continuous. So we'll say continuous on its domain, which is negative infinity up to negative 2. Hop over negative 2, negative 2 up to 2. Hop over that again, and 2 off to infinity. So essentially we're just finding domains for these kinds of examples, but we're doing so with a nod to the continuity theorems and remembering that there's a lot that goes on to make sure these things are continuous. Let's look at B. We know that radicals are continuous on their domains because we know that f of x to the 1 over n, that was from the theorem, that those are continuous on their domains. So we just need to figure out where the domain of this thing is, and it's continuous there. There are two ways to approach this kind of function. There's one that's super elegant, and if you happen to see it, I highly recommend using it. Let's start with that. Notice that we could call this y equals rad 9 minus x squared, and we could square out both sides to get y squared equals 9 minus x squared, and then solve it as follows: x squared plus y squared equals 9. And then we recognize that this is a circle. And then going back to our original function, a circle of radius 3, that is, right? But then going back to our original function, this is only the top half of the circle. Go back to y squared and then take the square root. This is only the top half. Because we're not getting the plus or minus in here, we're only taking the positive piece. So what this is the top half of a circle, like so. And you can clearly see that the domain of this circle is negative 3 up to 3, which gives us the domain of this entire function. Negative 3 up to 3. Done. Now, there's another method for solving these. If you didn't notice that this was a half circle, which is actually a pretty hard thing to notice, we know that only things greater than 0 can go inside of a radical like that. So then we just say, okay, 9 minus x squared must be greater than or equal to 0. And then we're essentially solving a nonlinear inequality, which is not entirely trivial. Let's factor this down. So we have 3 minus x, 3 plus x, greater than or equal to 0. And then technically we've done this in a previous class, but you have to do a sign chart, right? And then you test points in the regions. So we get our zeros here at, let's see, we have one at 3, we have one at negative 3. Remember this? And then you test a point in each region. We do x equals negative 4, and so on. X equals 0, and you test all these for positive or negative. X equals 4, right? And we're plugging them into these x's, and we're seeing if that result is positive or negative. And what we would get here is negatives out here, positives in the middle, and negatives out here, which tells us that we are greater than 0 right in this middle region, giving us the same answer, negative 3 to 3 again. So there's a couple different options for that kind of exercise. Let's move on to C. We have f of x equals the quantity x squared minus 2x plus 4 all to the 2/3 quantity. Well, let's rewrite this as a composition so it's a little more clear. How about this? X squared minus 2x plus 4. That's a polynomial. We know that's continuous. We know we can take a continuous thing and square it, and that's still continuous. And then we know from our most recent theorem that we can take a radical of something. I'm going to do that as 1/3, and that's continuous on its domain. Well, this is odd. So what does that tell us? So that tells us that we can plug any number into it, and it will still be in the domain. So going from inside out, we have all real numbers for the polynomial, all real numbers if we take that squared, and then all real numbers still for this 1/3 power. So this one is just all real numbers all the way through. So we'll write that as negative infinity to infinity. So I would say the exercises for this don't entirely capture the power of these theorems, but it's hard to capture them in an exercise unless the exercise is just having us do proofs, which we're not really doing at this point. So as you work through these kinds of exercises, do so with a nod to all the theorems that build up this complex machinery of continuous functions.